Hi, welcome to another lecture in the series of Advanced Material and Construction. Today we're focusing on textiles and their multiple and intricate relations to architecture. We'll start with this early work of Kengo Kuma, a floating tea house of 2007. And what we see is just a balloon and a floating boundary, a floating textile boundary, delimiting a space. That is actually all you need for a tea room, just a place for the ceremony, nothing else. And that's a canvas, that's an exercise for Kengo Kuma to define an abstract or an ideal material presence, which is this very light, extremely light organza, technical organza, a fabric that is delimiting a space thanks to the floating helium balloon. And this tension, this interrelation between the two is a temporary marking of a space and its connection to the body, to the person sitting inside. Let's hear what Toyo Ito is saying about this beautiful relation between the body, the space, and the textile.
おっしゃる通り、私の建築は、時代とともにスタイルも変わるし、素材も変わるし、形態も変わってきました。しかし、私の中で一貫しているのは、建築は人間のためにあるということです。多くの世の中の建築はむしろ人間がいない時の方が美しい、私は人がそこにいる時の方がより美しく見える建築を作りたいと考えてきました。人間がいて、そして、その大きな衣服のように人間を包み込む、そんな建築をいつも作りたいと考えています。仙台も三木本も確かにその構造をどのようなストラクチャーで作るかということには大きな関心がありました。そして、あまり他では見られないような構造の形式を使っています。しかし、そのこと自体が問題ではなくて、そのような新しい構造を採用することによって、そこにいかに人間的な空間を作るかということの方がより大きな問題です。例えば仙台メディアテックの場合にはのような大きな木の幹のようなチューブを何本も置くことによってその間で森のような空間を作る、森の中で人々が読書をしたりビデオを見ているような、そんな空間を作りたいと思ったわけですね。一方三木本の場合にはこれは商業建築ですからインテリアまで我々が関与することはできなかったんですけれども、そこにどのような光がどのように差し込んでくるか、それは見方によっては林の間から木漏れ日が差し込んでくるような、そんな自然のイメージという点では共通していると思います。トッツの場合は三木本よりもよりダイレクトに木のシルエットが構造体になっております。この建築の場合にはそんなに大きなボリュームでもありませんでしたし、ファサードが L 字型に折れ曲がっているというような問題もあり、その木のストラクチャーを全ての刺繍全ての面に連続させることによってこの木に囲まれたスペースというイメージをより強く表現したいと思ったわけです。私は随分前から建築と周辺環境、自然環境との間の距離を小さくしたいとずっと考えています。そしてできるだけ人々が自然環境から閉ざされたところで暮らすのではなくて、自然環境との連続的な空間の中で生活をしたり仕事をするということを目指して建築を作っています。
This inherent deep connection between clothing and architecture actually comes from Annie Albers, a textile designer of the Bauhaus, and she writes in the Pliable Plane about this inherent connection between textile and architecture. If we think of clothing as a secondary skin, we might enlarge this thought and recall that the enclosure of walls, in a way, is a third covering, that our habitation is another habit. So we have the first biological skin that we're born with, a second skin which would be our clothing protecting us, and another layer of protection that would be the third skin, and that is architecture. So this inherent connection between architecture, or the protection of man, and textile is already present from Neolithic age, as we see here from archaeological remains from around here, Mesopotamia. And you see already the work of man processing natural fiber and making a construction, a woven fabric. This richness of construction is already present here in the Bronze Age textile a bit later on. Remains that were very well preserved thanks to the fact that they were found in salt mines, and they preserve not only their structure but also color, and you see the variety of elements found within this archaeological site, demonstrating creativity, ingenuity in this engineered material. And Annie Albers writes later on, if the nature of architecture is the grounded, the fixed, the permanent, then textile are its very antithesis. If, however, we think of process of building and the process of weaving and compare the work involved, we will find similarities despite the wide differences in scale. Both construct a whole from separate parts that retain their identity, a manner of proceeding fundamentally different from that of working metal, for instance, or clay, where parts are absorbed into an identity. So these distinct parts that are put together to create a fabric, should it be building that create an urban fabric or fibers that create a textile fabric, that's the common point of both in their process, in their proceeding, in their construction. The inherent connection between textile and construction is not only evident with the machine or the technology that you need to make the textile or the loom, as we see here, but also in the very essence of the terminology. Textile is the same as fabric, and the word fabric, originating as far back as medieval times in ancient French, is directly connected to the notion of fabrica, or the workshop, a place where you manufacture and make things. So fabrica and fabric and textile are altogether this construction that is made of parts or elements put together. And this inherent connection between fabrica, fabrication, and textile is also present in the technology itself in the loom. So the jacquard loom, this impressive piece of technology as we see here, is referred as the first CNC machine. Well, how come? Thanks to these cards that we see here, the punch card. The punch card, invented by Joseph-Marie Jacquard in the early 19th century, is the first time that we have a physical, a material support that is used to transmit a design. So automatically with these punch cards, when you put it in the machine, you can repeat a set design that is being transferred on and on. So this is the first time that we have a numerical control over a machine that is not by hand, that is transferring a set design. Not only it can be repeatable, but also we have a direct control, pixel by pixel, over the fiber, which enable very intricate design that were not possible before, as we see here this portrait of Joseph-Marie Jacquard, the inventor of the jacquard loom, enabled by this technology of advanced weaving. So this numerical control is actually what enables the making of texture effect and structural effect out of the organization of fibers in space. Texture effects belong to the very structure of the material and are not superimposed decorative. Endless number of constructional effects can produce new fabric. So the arrangement of fiber in space is this constructional effect that Annie Albers refers to, and that's the very essence of textile construction enabled by this kind of machine, as we see the jacquard loom. Hela Jungerius, with her piece The Giant Loom of 2019, is taking this concept into a whole new dimension, and she's making a giant vertical loom in this 3 stories high space. And she's writing, the reason why the space loom is so large is because it responds to the question of scale and how to inhabit the verticality of the building. And because the building's architecture is essentially a machine, it made sense to use it as a weaving machine, a loom. So here she refers to this Corbusian notion of a building as a machine, putting it together with the notion of Annie Albers of placing fibers in space as a construction. And you have this inhabiting of space, a very unique inhabiting of space by the giant loom that is changing altogether the perception of space and the making of textile on a whole new dimension. With this giant loom, Hela Jungerius is also placing the contemporary aspect of weaving, and she is saying, a woven structure is the strongest and lightest material that you can get. It is, I think, a material that has a high-tech future. And we need this high-tech future to face the challenges that we have today. As traditional building materials pose more and more ecological problems, industries are exploring the potential of mass production of 3D textile to replace these, with woven fabric being a light, strong, and sustainable alternative. So facing the sustainability challenges that we have today and the problems of materials that we have, the possibilities that are offered with the 3-dimensional textile or their weaving is enormous, and that becomes a high-tech material that is adopted by more and more industries. So it all relies on an internal structure, a 3-dimensional spatial arrangement of fibers. We see here a zoom in on the top of knitting and on the bottom of weaving, and it's a completely different arrangement of fiber that actually determines the mechanical behavior of the material, its stretchability, its ability to distort, to resist tension in this or other direction, its stiffness, and much more. So we have a parametric control over the behavior of the material at the level of the engineering of the material itself. And this engineering is very accessible, it's rather simple, and it's rather direct. Weaving is primarily a process of structural organization, a structural organization of the material, as Annie Albers is saying, that determines its performance. And this is elaborate in technical textile, as we see here. We have loads of 3-dimensional arrangements of fiber for different applications or performance requirements, from knitting that is highly stretchable to braiding on the upper top, that is twisting the material to a tubular arrangement, and to many other 3-dimensional or 2-dimensional weaving, triaxial or 0-90 degrees, all of them used in industry, in various industries such as composite industries that we're going to see in the next chapter. And we see here 3-dimensional structure elements that are woven on the right from carbon fiber, and artistic 3D weaving on the left, where we have yet another dimension, not only the 2-dimensional structure of the making of the textile, but a 3-dimensional structure made by the weaving itself. This work of 3D weave of a Schenkau student, graduation project, demonstrates the possible intricacy and way to master the 3-dimensional construction of an element through weaving. This is actually a 3-dimensional piece that is getting off the loom as it is in this way, and it's all by planning. There's multiple layers that are connected together in the making of textile in 3-dimensional space. From this masterpiece of craftsmanship, 3-dimensional piece made by hand weaving, we go into industry. And here we have a 3-dimensional knitting of fiberglass yarns. It's a spacer fabric that we know from sports shoes or sport bags. And actually this 3-dimensional arrangements and structure enables also flexibility and porosity. It's very light, but also it can transmit or keep heat and humidity as required. So by layering and structuring the material, we have material with more and more intricate and extreme performance requirements, such as keep us warm but transfer our humidity or our sweating, but also not enable the entrance on the other direction of humid or fluids like rain. So we have extreme performance textiles that are made just by arrangement of layers of these different structures. Here in the spacer chair of Door Design, this material is used for its structural capacity, so it's porous, it's light, and it has a three-dimensional structure, and when it is hardened with resin, it is highly structural. And we have this folded line of a very thin layer of fabric that is actually structural and making this beautiful spacer chair. So just as chemical treatment has produced fluorescence, is saying Annie Albers, so structural treatment can produce, for example, sound absorption. So structural treatment, that's the three-dimensional arrangement of the fibers in space or the construction of textiles. And we know that textiles are very good materials for sound absorption and acoustic elements in space. If we see the work of Anne Kiroquin over the years, she is making these beautiful interiors, highly aesthetic elements made of fabric that are also sound absorbing and have acoustic role. She's doing that by pleating of the elements, and she's using felt material to make these meeting rooms or auditoriums that have good acoustic qualities. Here you see a zoom in of the felt material on the bottom, and it is compared to the structure, the woven structure that we saw before. So while woven structure is the clear arrangement of these fibers in 0-90 degrees in warp and weft, a non-woven fabric, which is the felt, is kind of spaghetti mess of fibers amassed together, as we see here. And this is exactly what makes this material absorbent. So we have the sound waves that hit this material and through friction are transformed into heat or to thermal energy, and they are not brought back to the space, they are absorbed. So that's the absorption of the material of the sound waves. Here in this research, we see the comparison. So on the bottom, you have the dotted line, which is a woven material, a non-woven material, bare as it is, and all the others as the combination of this non-woven material with different types, different structure of weaving. So the combination of both improves significantly the sound absorption of the material, and also additionally, you see the influence of the different structure of the woven material over the level of sound absorption of the material. So by a simple control of the structure of this textile material, we can actually affect the level of performance that we get from the said material. Again, Samira Boon, but here using textile for their acoustic properties and not just by the structure of the material itself on the micro level, but on the macro level of the space itself. And she is making these acoustic elements by pleating of the material, and this time the sound absorption is achieved on a much larger scale with this piece. Going from the abstract idea of architecture as the extension of our protection or our clothing to the actual performance of the material itself for its acoustic capacities, for example, as we saw before, we have various multiple layers in which this textile material appears and is present in architectural world. So a theoretical model, a design paradigm, and a material presence that accompanies us along architectural history. Starting with the theoretical model, we have Gottfried Semper introducing this idea of the knot or the wrap, the textile wrapping, which is the very basic human design or artistic activity as he represented symbolically. So it's wrapping or putting together a few elements, making it an object. And also this alternative of the Caraïbe hat that is presenting to this idea of architecture, the origin of architecture. And at the origin of architecture, according to Semper, there is this native Caraïbe hat with a textile enclosure in the walls. What delimits and defines space is fabric, is textile. And he takes this idea of dressing of the space to the concept of Bekleidung or cladding, and the dressing up of the space is very present in the contemporary of his time, Otto Wagner, and his architecture, which is highly decorated, ornated, alluding to textile elements. And it is this idea that you're dressing up the building as you are dressing up human being, and it's part of the language and the message that is transferred. And although Wagner clad his building in ceramic style, as opposed to real cloth made of woven fibers, one might still understand this covering as textile that functions like clothing for the body, both by physically covering the structure and by alluding to other forms of fabrics. So this jumping between a textile that is made of ceramics or covering off the building that is kind of a clothing is actually goes very much in line with the theory of 4 elements of architecture of Semper himself. And Semper actually divides the Carib hat into 4 fields or 4 human activity: masonry, carpentry, ceramic, and textile, each manufacturing or creating a different element in the Carib hat. But the ingenuity of Semper is by saying that every division is to be taken in its broadest sense, which leads to a number of mutual relationships. That is, that masonry or textile are not only directly associated to the typical material that is used for this craftsmanship, but also it is a way of processing. Such forms will therefore be stylistically assigned to one or another technique according to whether their formal or material properties are being considered. So we can imagine, if we are transposing this idea of Semper, that we can create a textile or a ceramic that is not necessarily made by clay or fibers accordingly. We can imagine an urban fabric, we can imagine a metal fabric, but has the properties or the logics of textile making. The groundbreaking idea of Semper, of this division of processing ways that is at the heart of the design and design activity, is taken a step forward by Bernard Cache, a theoretician of digital architecture. And in his essay Digital Semper, Bernard Cache is actually taking these divisions of Semper that we saw before, the textile, masonry, ceramics, etc., and transferring those into yet another realm, which is not the realm of fibers or clay, but the digital realm of information. And here, information, bits and bytes, are manipulated in the processing way of matter. So just as the way as the weaver would arrange fiber materials in space, digital code is arranging those bits and bytes in a spatial arrangement, in that case a parametric arrangement in Grasshopper, that would give us an arrangement, making of textile. And this parametric control is actually bringing a design paradigm that is based on textile into our design world. The paradigm of textile actually goes to the very basis of the thread. And as we see here in the sculptural work of Chiara Sciota, she is populating the space endlessly with this fiber, actually creating a negative space, which is the void of fibers. That is the element that she is representing. And this idea that you could create a space, either negative or positive, is taken by the ICD in Stuttgart in their continuous research of fibrous structure. So here the fibers are structural and technical. It is either carbon fiber or glass fiber, lately also flex fiber, as I will see in the next session. And here they are making a space made of these fiber elements in a 3-dimensional arrangement by a robotic arm, space that is airy, structural, stiff, strong, making those beautiful elements that are very translucent, transferring air and light into this enclosed volume. And this very last piece of the Venice Biennale demonstrates how these elements could be transformed into structural element, creating some kind of traditional rectangular space, as you can say. And it is enhanced by this opposition with the existing traditional structure of brick of the building itself, where exhibition is set, that is very heavy, opaque, and in opposition to this very airy and light structure residing on fibers. Losing orientation, blurring boundaries between material and scale, introducing new structure. This is the potential of textile entering into the architectural world as a design paradigm. Here, in the work of Lars Spybrook with his students, The Architecture of Variation, they are taking textile structures like braiding, knitting, weaving, studying them, making some kind of a code, introducing variations into them, thereafter to be an architectural project. We know architectural projects taking the realm of fibers and textiles into the realm of metals, like this metal weaving, or yet another example of other metal weaving here in the office building in Tokyo, where you see this very simple up and under structure that is not only airy and beautiful, but also structural, making this architectural facade that we see detailed here. Another example of textile pattern taken into the architectural world is the work of Shigeru Ban. All along his career, he's playing around with this Chinese hat and the kagome weaving, the triaxial weaving, translated into different appearances, mostly in wood, as we see here also in the Pompidou Metz. Now, it's interesting to have a closer look and understand what happens when you scale up and you change material, because you can no longer have the thin fibers just crossing each other up and under in a junction like this. It gets much more complex as you have beams interlocking or crossing each other. And in this case, let's have a deeper look here, and you see that the fibers, so to speak, are doubled as beams. And these beams that are curved in three-dimensional space are crossing each other in a very complex manner. And one can ask itself, what is actually the meaning beyond inspiration, beyond beauty, and beyond pattern? What is the meaning of the transformation or translation of one design or one pattern in one material into another material realm, and what's the meaning of it, and does it actually serve as a technological transfer or not? While this transformation or this shift might be arguable, when we have a look at an earlier work of Shigeru Ban with textile, we see an actual paradigm shift when using the material itself in a whole different architectural context. And here you see that he's just playing with the idea of a curtain. We all know the curtain, and it's actually realized in the very similar way to what we know. However, its scale is different and its position. Not indoor, not in a room size scale, but on here as an envelope and an outdoor positioning. And just this simple act, the scale and the positioning as an envelope, actually generates a paradigm shift, a shift in the way we understand interior and exterior space, a shift in the way we treat the neighboring environment, and maybe questioning the topic of intimacy, the notion of intimacy, and creating this in-between space in the house, which is nor exterior nor interior, partially intimate, but also very close and very exposed to the outdoor space, and all that with this semi-stable envelope of the house. Because of people's familiarity with the material, there is a great potential to deploy existing techniques, skills, and cultural resources to develop a 21st century manufacturing model. Thanks to this intimacy, this natural intimacy that we have with the material, one can get sometimes strong and meaningful paradigm shifts with simple moves. And this questioning of all the notions that we know of something that is so familiar to us, is exactly what Do Hossō is doing in his installation. Thanks to an extreme control of draping and patterning of this flexible polyester material, he's giving us this illusion of an architectural volumes, of elements that are stiff, that are stable, that are protective. And one question itself, what do we see actually? Is this a space? Is this an architectural space? Is this a stable home? Or is it even a virtual space that we are in, as it seems here? This blurring of boundaries is exactly what Lily Reich is doing to Mies van der Rohe early in 1927. So in this very modernist, clear, obvious modernist space of Mies van der Rohe, in this collaboration, Lily Reich is introducing draping. Velvet and Silk Café is about a subversive introduction of these textile elements into space, heavy draping that changes our understanding of interior, of partitioning of space, or our relation and intimacy with this element or interior skin of the building, And this is thanks to this duo collaboration between the two. This is actually a model for the collaboration of another couple that we know, Petra Bleis and Rem Koolhaas, and they're collaborating through OMA and Inside and Outside, and she is introducing constant questioning of the spaces of OMA. Like we see here in the early example of the villa, look at this contrast that we have between the Corten facade and the very delicate flowing element of textile that we have in the boundary. It's not only introducing translucency and a different geometry and a dynamic, but also an idea of flexibility. You see here the railing. So it could be changeable, it could react to the user, it could change according to the time, according to need, according to a season, and that's a sharp contrast to what we know as our stable and rigid traditional architecture. This play between the two is present all along their collaborative work. Here we see another example, and they take the care to demonstrate this with the user, changing the elements. Petra Bleis is bringing all her knowledge of textile design and advanced textile materials into architectural space, interior and exterior as well. And with that comes also the ornamentation. We've been mentioning that before, so inherently linked to the textile world, also creating intriguing and very unique situation, as we see here, of transparency, of partial separation, and of fluidity. Questioning further on, here we go into questioning our gravity, or our sense of gravity, and the way we experience space. Newman Group are playing around quite a lot with the way we experience space. Here in the installation Floating Landscape, where we have tensile tension nets within the boundary, the interior boundary of this patio of a classical building. And adults are called to experience space in this very playful landscape, and we are called to question our sense of stability, our sense of orientation, and the way we experience gravity on ground, solid or not. This playful experience with nets is also taken in the Brazil Expo Pavilion in 2015. See here how this huge tensile net is actually transforming the space into a huge playground, and the audience, the visitors, were invited to go and experience the space quite differently over this net. Blurring the boundaries with the design paradigms introduced by textile, we can also blur the boundaries of what we consider as textiles. As we see here, for example, the stainless steel curtains introduced by Knox, beautifully draping the exterior of this building, that could be textile too, just as the ETFE foil, a flexible, translucent, transparent element. It's not a textile structure, and yet again we could relate to that as a textile material, and that's actually a technological transfer all the way from NASA to architectural world, first introduced here in 2000 by Grimshaw, but since then in multiple and numerous architectural applications, thanks to extreme properties and characteristics this material is bringing into architecture. from textile as a design paradigm or a paradigm shift in architecture world, we'll focus now on the material itself, textile material presence in architecture. And textile actually behave in a very particular manner, in a very particular structural scheme. We see here the categorization of Engelheino. We have 4 categories describing how a structure is dealing with external loads or how it transfers it into the ground. So while we have a section active element which transfer the loads through the thickness of the material itself, it could be a slab, it could be a beam. We have a surface active element, that is the shell. Loads are actually transferred over the surface to the ground. Textile is typically a form active system, and in the form active system, it's by the geometrical form itself that loads or external forces are dealt. So we have an application of shape to the material. It's by pre-stressing or pre-application of a stress, and this pre-stressing of the material, it is resisting the external loads, and that's actually the structural stability and stiffness of a textile material as it resists external loads. Typically, it could behave in 2 ways, either as a tensile structure, applying tensile stress over the material, as we see here, the stockings, or a pneumatic structure, applying compression through internal pneumatic load, air pressure, as we see here in the balloon. The basic typical pneumatic structure would be a balloon. We have internal pressure from the center towards the boundary of the shape, in that case, a sphere. This is actually one example out of many. From the 60s onwards, designers and architects are playing around with this idea of a minimal shelter, a lighter structure possible, and they're excited by this structural principle of form active, which is enabled by this material, the polymer membranes, which are also, in that case, translucent. This excitement is very present in the Expo of 1970. And we see few examples of pneumatic structures of different kinds. So here in the Fuji Pavilion, we have an air inflated structure, and that means that each of these orange sausages, quite huge actually, 4 meters in diameter, 70 meters long each of the arches. So each of them is inflated separately, and they are assembled to form one coherent structure. The span is free, no support, but also no air pressure within the space. On the other hand, we have the American example of the US Pavilion, and that is an air-supported structure when you have one whole space that is under pneumatic pressure, and once the structure is totally inflated, then you get your structural stability and the stiffness. You see here this example of the iconic Tokyo Dome of Kenzo Tange, more than a decade later in the same place. And you see the gradual inflation of the structure towards its final fully stable shape. Still today, we are actually excited by these kind of structures, but this time it is with a new material, and this is the ETFE. So this iconic example of Allianz Arena. Each of the cushions is maintained under pneumatic pressure separately. You see these channels of air supply that also make sure that cushions are maintained under pressure and are therefore structurally operating, structurally stable. And another characteristic of the material is its translucency, and in that case they take advantage for that to run lighting, LED lighting, that is also changeable according to the teams playing in the football arena, so you have the colors of the playing teams. Another example, more or less at the same time, the water cube. Here it's a double layer, also under pressure, and in this case it regulates not only the light that enters into the structure, but also the thermal comfort, humidity and heat, and it encourages natural ventilation through the structure itself. And to conclude, we have the recent addition to New York, the shed by Diller and Scofidio, where you see this huge shell, ETFE shell, and thanks to the lightness of this material, extra light, this piece is also movable, enabling a totally flexible program and usage of the space, quite unique in its dimension and characteristics. Let's have a look.
It's basically a crane. It's a fixed building with multiple levels of column-free floor plates and a shell that's able to nest and deploy on the fixed building. And when nested, opening up a big open space. When deployed, could be indoor, outdoor, have a flexible space where the elements could come in, or have a totally sealed, thermally controlled footprint that's also light and sound controlled.
One of the unique aspects about the shed's diagrid is the facade system. The facade is made of ETFE, it's ethylene tetrafluoroethylene. It's a Teflon-based polymer that is fabricated similar to a sail, where they have sailmakers cut the patterns, weld seams, and they bring them to the site rolled up. They attach them to the steel frame, and then they inflate the various layers. It can span as long as you can fabricate it, and it can resist tremendous wind loads. It's very resilient, where something rigid like glass or fixed panels wouldn't be. So whatever torsion the shed finds when it stops and starts is easily absorbed by this pneumatic cushion. If you compared it to glass, not only is the material itself 1/100th the weight of glass, but it doesn't require any of the backup structure that you would typically see. I would say we probably saved 30% of the weight of the shed through the use of the ETFE. This geometry it's very straightforward when you think about the load imposed on it, right? The gravity loads, there are vertical columns that all go back to those the wheel assemblies. So the vertical structures handling that. Wind loads coming from, we'll call it the east or west, these diagonals are taking those loads and making the frame rigid.
Another really very important feature is that because the shed is actually a gantry crane, you have to be able to haul things up and down and across and so forth. So we have this idea of being able to load very large sculptures or building materials actually through the facade and be able to use the shed as a crane to move materials up and down. So we were thinking about this whole thing being an instrument for producing art, for making things, for installing things. This was a kind of labor of love to massage this design to be clearer and more efficient, but at the same time very elegant and expressive.
One of the key things about I've certainly learned through my experience with the shed is we're never smart enough to predict the future. We give it our best shot, but with technology at least, when we have open platforms, we can change as technologies or tastes or trends do. You know, I think that's the way we're going to be designing neighborhoods in the future. I think that's also the way we've tried to design the shed, is as sort of open architecture-like as possible so that it can adapt as times change.
One of the big problems with architecture is that it's geofixed and it's permanent from the moment of its construction. This building is responsive. It's kind of paying attention to things and trying to accommodate and prompt as well. It would be interesting to have a conversation between the building and artist. And that's the thing that I look forward to most, is the things that I can't possibly dream up. And I would really love to be surprised by things that I couldn't imagine right now. I think the building will be successful only if it produces things that we can't anticipate.
I like this view of the advanced structure, the installation of Anish Kapoor, the Leviathan, placed within the advanced structure of the time of the 19th century, the Grand Palais. And you see how the innovative use of the time of steel and glass offer large spans and light entering into the space. And here, once inside the space of Anish Kapoor, it is an air-supported structure, so public is invited to go inside and appreciate the sensorial qualities of this inflated membrane that you can also see through and have a glimpse at the general structure of the Grand Palais. And following Anish Kapoor, here we are at the Tate Modern, and this time it is a tensile structure. So Anish Kapoor is playing around with innovative structural principles, and here is populating this huge turbine hall of the Tate Modern with this tensile structure of Marsyas. And the whole space with this huge sculpture is actually defined just by these 3 stiff rings that are placed in the extremities of this weird shape, one can say. And well, it's not only the 3 rings that are that constitute the boundary condition, but also the fine patterning of the stretch membrane that is adapted to result in the desired shape once placed under full tension. So not only the desired shape, but also the structural performance. So once in full tension, this is stiff and structurally stable. This interplay between material properties and tensile forces or gravity is what this crochet playground is based on. And this beautiful handcrafted work of crochet offering a playground, colorful, playful for kids, playing with gravity and the tensile forces and offering these very unique shapes. This is also the kind of materials Ernesto Neto is working with, gravity and tension, but here with lycra fabrics, he's playing with the translucency and colorful aspect of these materials and a minute control of the resulting shape by pattern and by the weights he's placing, offering this dreamlike atmosphere. A very sharp jump would bring us to more technical aspects of these elements. So here they're used as advanced facade for the King Fahd library, and each of the elements is individually under tension, offering self-shading of the facade and regulating by that the thermal comfort inside the building, shading and airflow controlled through the stretch membranes. We also know that from El Bahar Towers. Here it is fiberglass coated mesh, so very light and flexible material that is stretched over a frame over each of these movable component that would adapt according to the changing external climatic conditions. Here you see this kind of textile patterning of changing components parametrically according to the external conditions. Maybe this huge mega tensile structure of Khan Shatir is alluding to the nomadic characteristic of these tensile structure, basically a huge tent, so huge that the basis is 200 square meters. I think it's the largest single tensile element that we have till today, reinforced with these metallic cables that enables the structural stability of this 150 meters high structure. Nomadic quality is also very present in the program used mainly for exhibition spaces. The temporality of these elements, you can very easily erect them and then dismantle as needed. Here in the Shanghai Expo, the whole central axis of the Expo was actually made by tensile elements, these kinds of inverted umbrellas, offering a free span, extreme height and flexibility, with this temporal aspect. Using tensile structures as temporary elements for large exhibition is probably a take on Frei Otto's innovative multi-hall at Mannheim in 1975. And here he's doing this huge exhibition hall with a free span thanks to the innovative structural principle of a grid shell. Over this wooden shell, grid shell, he's placing a textile membrane, and that's what offers this huge, very innovative space. But there's yet another aspect of the usage of textile in this project, and that is using textile as a structural model. And what Frei Otto is doing here, he's using this net, this fabric, as a structural model, because he cannot use computation to have form finding process to understand what would be the resulting shape. He doesn't have computer, and therefore he needs an analog computer, which is a physical model of this hanging structure, to understand what would be the mirrored image and shape and structural behavior of this grid shell under compression once fully structurally performative. This is an ancient tradition, actually, starting from Robert Hooke already in the 17th century, where he understands that placing this chain under gravity, that's a catenary shape, would give him the mirrored image of the exact opposite under compression would be, that is the arch. And from that we have the legacy going on to Antoni Gaudi doing these elements of the Sagrada Familia also with a hanging model, and to that to Frei Otto in the 70s. And Frei Otto is extensively studying the behavior of materials under minimal condition and gravity, form finding a self-organized shape according to the boundary condition. Here we have the example of catenary textile surfaces, so placed under minimal boundary condition, and thanks to the size and quality of the specific material, you get the specific resulting shape. This is exactly the discipline used here by Musmeci, also in the 70s, to find the actual final shape of this concrete bridge. So the Basento Bridge is also using a physical scale model of concrete to understand what would be the final behavior, the deflection of this concrete membrane. But you see the resulting shape. Here still today in the southern of Italy, it's some kind of a stretched concrete membrane, if you wish, offering stability and elegance thanks to the way it was designed or form found. The master of this discipline is probably Heinz Isler, the Swiss engineer that is making hundreds of concrete shells. Highly efficient concrete shell thanks to the process he's using. So he's also doing a hanging membrane, placing gypsum and defining the resulting shape. Once the shape is, the element is stiff, he is inverting it, and you get to see the similarity between the model and the final outdoor theater that we have here. All of the shells of Heinz Isler are extremely efficient and elegant. See the very thin section of these shells, of the concrete shells, and that is mainly thanks to the way their form is defined. It's not by imposing an external designer or engineer wish, but by form finding the self-organizing principle of the material that would be its most efficient. We see here this very rare diagram, a monitoring of the shells of Heinz Isler himself. He's monitoring the deflection of these elements over time. All structures have deflection. But what's interesting to see here, though, he is actually placing those in few different categories. And the category of the hanging models, hanging membrane models, is actually the most efficient one and the most stable one. So the ones that are found under this principle are also the one that would last longer and would be the most efficient. I mentioned Heinz Isler is Swiss, so he lives in Switzerland and he's playing in his garden, in his yard, with this stretched membrane that he's spraying with water, and he's creating those icy shells as a play. But actually what he's doing, he's not using the fabric only as a model as we saw before, but here we have a textile mold. So a textile mold is a principle of using a fabric tailored for fabric former to cast concrete within it. So this final shape is actually the computation between the characteristic of the mold and the fabric and the weight of the cement. And it has not only tactile and aesthetic qualities that are unique, but also a capacity to be highly efficient, because you could tailor your mold very easily according to the structural forces that is running in this specific element, as we see here, this efficient concrete beam in a textile mold. Textile as a mold is being developed still today under robotic fabrication, as we see here in the fabric forms. Let's have a look.
trying to explore a different side of architecture. There are certain architects who design something simply through a form. It doesn't really matter in the end if it's concrete or metal or wood or whatever. The primary importance of the project in their mind is the form. There are others who might be more interested in the fabrication, and everything is subservient to that fabrication process. For my practice and the kind of the heart of it, the name of it being material systems, the approach is that there is an integration between form, growth, and behavior. Any living creature or non-living thing in the world, any naturally made thing, from a mountain to a river to an ant or a human, we're all made through this combination of form, growth, and behavior. So in making Keywall, I started looking at the work of Miguel Fisac, a Spanish architect who worked in the 1950s through 1980s. When we look at concrete, we think of its solidity, its mass, its weight. The average person doesn't realize how fluid concrete is as a material. Miguel Fisac, with his work, really began to express that fluidity of the material, because as the liquid concrete was poured into the form would change shape, and there was this relationship between those two materials. So how could I continue that expressive nature of the material, in this case plaster rather than concrete, using an elastic fabric which would expand and really speak to the material forces? So the fabrication process is fairly simple. It's really the interaction of the constraints and the elastic fabric that's over them and the plaster that we put in. We change the constraints around, which are just wooden dowels based on the density of the number of holes that we want in the system. And we take the mold apart and peel the fabric off, which is spandex lycra. Clean the molds, then rearrange the dowels according to the kind of master pattern that's been developed through the computer algorithm.
The natural ability of textiles to self-organize and form efficient structures stand at the basis of quite a few research looking to find alternative modes of fabrication that would be more efficient and more sustainable. This is one example, the Block Research Group at the ETH. So here, fabric is under tension, it forms a minimal surface, concrete is cast over this flexible mold, and the resulting shell is with a minimal section. It's really, really tiny and very thin and elegant. So on this basis, they moved forward up in scale to the ambitious project of the high-low nest. Here they took not only fabric but also cable knit together under tension to form the mold. And on this the concrete is cast, and integrated within it is, here again, textile, but this time as a reinforcement. Still at the Block Research Group, here we see the project of Knit Candela. This is a homage to the master builder of concrete shells of the 20th century, Felix Candela. And here again you see the textile with quite a few purposes. So first it is of course the mold. The knit fabric is under tension, and this is the mold. And it is actually integrated within the final concrete element, so it is the stay in place or lost form. Both terminologies are relevant. And on top of everything, this is also an aesthetic element. So you see the patterning. All the purple fabric that you see is actually the knit mold. One step further in this combination between textiles and concrete, we have the concrete canvas. So here, the fabric itself is impregnated with the cement, a dry mixture, and once it sprays, it actually forms a hard final concrete element. So it's very convenient for quick emergency shelters, as we see here, but it is mainly used as geotextiles. That is for the reinforcement and stabilization of large landscape elements, as we see here. And this actually leads us to the final combination of textiles and architecture, which is textiles as reinforcement. So the use of textile as reinforcement for an architectural element here in the textile reinforced concrete actually reminds us of what we see on the left. So this is a composite material that we all know. It's the reinforced concrete, the combination, the magic combination between steel and cement, the rebars and the cement mixture. Together, they form a very powerful material with a good performance, which is the reinforced concrete. So fabric could act exactly the same, replacing the steel rebars. And this is actually leading us to the topic of composite materials, which is the topic of our next lecture. So next time we're going to examine how two elements perform together as a composite material and what it enables in architectural terms, in terms of structure, of strength, etc. Thank you very much. See you in the next lectures on composites.